about what blockchains are and how they work, and maybe convince you that you probably don't need one in what you're doing. So maybe first off, I'm interested to see a show of hands of who thinks they know how blockchains work. Can you put your hands up if you think you do? Excellent, this is the right target audience. So I'm going to start by giving you a fairly lengthy introduction to how they work at the technical level. And then I'm going to talk to you a little bit about what the problems that blockchains are facing today are. The two major problems that I see are that of the privacy of blockchain systems and the scalability of them. And then finally, I'm going to talk a little bit about, well, what I actually say in the title of where is the hype coming from and why do you maybe not need to care about it. So in talking about blockchains, it's a quite intrinsic connection to make with the idea of consensus. And consensus is a difficult topic to get a handle on, but at its core, it just means that people are agreeing on something. Now, there's several levels you can agree on something with, and I'm not going to focus on the level of how do we decide on what should be. So I don't care if your voting system is first past the post or proportional. Okay, there's only one of those which actually works, but that's not the point of this. The point is, once, say, a vote has taken place, how do people reach agreement on what actually happened? And this is more of the core of what blockchains do. They're not a system for deciding what should be, they're a system for deciding what happened. And how this is typically presented as an introductory issue is with the so-called Byzantine generals problem. And this is a fairly straightforward setting. You have, oops, wrong button. This is the right one. You have a city which is being besieged by 4 armies. Each army has its own general. And the core of the problem is to say, well, if these armies attack together, they will conquer the city. If some of them attack without the others, then the defenders will defeat the armies and the city will remain standing. Now, clearly this is a toy computer science problem, as these problems usually are, but it has a lot of real-world connection because the core of this problem is the armies need to decide when to attack. And moreover, they need to decide even though some of the generals may be traitors. And so this is a situation where you have 2 treacherous generals here in the bottom left and the top right, and it should be clear to see that in this situation the generals cannot win. Now, the most obvious reason they can't win is because they don't have the manpower to win, so if they try to attack now, their opponents will take them down, but it goes beyond that. Because what can happen in this situation is if these generals are trying to decide when to attack, let's say this general wants to attack at 1 p.m. and this one at 3 p.m., then these 2 can pretend they agree with both of them. And so they can convince both the top left and the bottom right general that they're going to attack together with them. And these will probably think that the other one is the traitor, because that is the only general that's not agreeing with their plan. And as a result, they don't attack at the same time. Now, fortunately, it turns out that if few enough of the generals are traitors, it's possible to identify this, and it's possible for the rest of the generals to agree on a time. I'm not going to tell you how they do so, but you can imagine that they just send suggestions back and forth until they agree on something, and they have to have some way of filtering out the noise coming from the traitors amongst them. Now, this is very nice in theory, and this was the state of the art for a long time in distributed systems literature, but it turns out that in practice, what we want is more. We don't really care about a small group of people agreeing on when to do something or even agreeing on more complex issues. What we really want to get in order to have a global system is we want to have global agreement. So we want the world, for example, to agree on how many funds I own in some currency system. And that turns out to be difficult. And it's difficult because you can't identify people. So you may say, well, we just have every person be a general. But on the internet, no one knows if you're a dog, or more dangerously, no one knows if you're a botnet. Which means your botnet of a few million computers has essentially the same standing as a few million actual users. And that is not a situation you want to be in for any kind of distributed protocol. If you try to run BitTorrent and you try to attack that with a botnet, that will go down. But it's far worse for a consensus protocol. Because in a consensus protocol, not only does the system go down, but you no longer have agreement. And you can never reach agreement if you have the system being attacked by most of its users. So it turns out this Byzantine generals approach and the solutions that have been proposed in the literature for it don't really work in the setting that we want to build cryptocurrencies in. So what can we do? Well, we can't trust that most users are honest. And that is the core of the Byzantine generals problem. We have to assume that at least 1/3 of users, if you want the precise number, act honestly and are not traitors, as I put it previously. And we can't assume that. The reason we can't is it is very difficult to identify people with an algorithm. What we can identify instead are resources. And there's a couple of resources that are quite easy to identify. In particular, computation power is easy to identify. Another resource which is easy to identify is money, if this money is already stored in some digital system. And so what Bitcoin does is it uses computation power to underpin the security of the system. And it assumes that most computation power is honest. Now, the way it does that is by using proof of work. And proof of work predates Bitcoin by quite a bit and was originally designed as an anti-spam mechanism. The core idea is that if you have some message which you want to send someone, so I want to send an email to, let's say, the room here, that's probably a bad idea because then I'll have to put in a lot of work for everyone in the room. But say I only want to send an email to one of you. And I want to make sure that this gets through your spam filter. The idea was, well, if I have my computer work on this for an hour or two, then that should be enough to convince your spam filter that this is not just some mass mail that I sent out to everyone, but that it's something that is actually targeted to you and that you can probably, spend the time to actually read it. So what is it at its core? Well, it relies on hash functions, and in particular, it relies on the randomness of the output of hash functions. So your typical hash function, h, will have an output domain of lambda bits, and the idea behind the proof of work is to try to find some pre-image which hits a target. And, well, if you want to put a proof of work on a message m, then you say, well, I take a hash of that message as well as some nonce which I can try again and again until I hit this target. Because as it turns out, it's quite unlikely to hit it the first time. So what this target is flexible, and it depends on how much work you want to emphasize you've done. And the basic idea is you want your hash to have a certain number of zeros at the start. And if you have m zeros at the start of your output hash, the probability, if you just hash once, of getting that is 2 to the minus n. So the more zeros you have, the less likely you are to hit this by chance. And for numbers that are actually used in the real world, you will usually have at least 40 or something zeros preceding the hash. So there's really a very slim chance of 1 in a trillion or something of that kind of hitting this by chance. What is more likely is that you've actually gone and tried trillions of times until you found one which does work. So okay, you can use this to, if you have a message, you can use this to essentially put more emphasis on it. You can say, I have worked to make this message important. You should consider it, therefore. And this we can now use to build the actual blockchain. Now, the term blockchain, I think, is a bit too grandiose. This is a blockchain, or, well, a rendition of it. It is a singly linked list. That is all a blockchain is. You have some unique item at the end, marking this is the end, and the rest of the items consist of a data field, consist of a backward pointer. Typically, this is a hash of the previous item, because this is a network data structure, so we can't use physical pointers. And then you have this third item, which is the proof of work itself. So this is the part that says, I've worked on this, please consider it important. And so every user in Bitcoin or most other blockchains will maintain one of these locally, and this is what they consider to be the truth. At the start of the protocol, there will just be the genesis block or the end of the list. Now, the protocol itself now works by every user trying to extend this. Every user will try to create their own block and try to add to this already existing consensus. And so how does this work? Well, you take your existing chain and you create a candidate block. So you choose what data you want in it, you select the right backwards pointer, and then you start doing a proof of work on this. And you keep going until you find a valid proof of work. So until you find a hash with a nonce of, and with the message of the data field and of the back pointer, such that it falls under a target. Now, once you've found this, you send it to the network happily, and everyone else is at least instructed to adopt this as well and start working on that instead. So also by, how do you phrase that? That also implies that if, while you're working on this, you see a longer chain, or a chain with more work on it rather, coming in from the network, you drop what you're doing, you create a new candidate block on that one instead, and you start working on that. So in practice, you will get a chain like this, and that, of course, doesn't mean that everything is perfect, because it can very well be that two users coincidentally find a block extending the same prefix at the same time, or at a very close point in time. And at that point, the network as a whole is not sure what it wants to adopt, because these have equal weight. Fortunately, the statistics turn out not to be that bad. It's quite unlikely for both of these to then get extended simultaneously as well. What's more likely to happen is that one of them gets extended before the other, since the proof of work process is stochastic, so it's very likely that someone will get it first, even if everyone is equally matched. And then the network will collapse on this one and will completely abandon the bottom option. Now, that is, of course, only for the accidental problems that come up. What's more interesting is if someone attacks the network. And an attacker can take more risks, because an attacker might want to do very specific things. For example, I might have made a transaction here, giving one of you a lot of money, and I might now decide, why did I do that? That was a bad decision. Let's pretend that never happened. I never gave you anything. And I can now start working on an alternative history where I didn't do that. Now, as an attacker, I am now disadvantaged, because I need to come up with 5 blocks. Actually, I need to come up with 6, so that people actually consider mine superior to the one that's already there. And I need to do this before any honest users extend this. And it's possible for this to happen. It is, after all, a statistic process. But as this sequence gets longer, as I try to change something that is deeper and deeper within the chain, the laws of probability are against me. I get exponentially lower chances the deeper what I'm trying to change is. So that's the basics of so-called Nakamoto consensus and proof of work. I'm going to make a very brief pause here and see if there are any questions on this particular part.
Just a quick one. You
Yeah.
mentioned nonce.
Yes.
What does that mean?
So the nonce here, so the thing is, if you want to make a proof of work on a message, so the proof of work consists of showing that some hash of the message and something else is less than a target. And the reason we need the and something else is because if this doesn't exist, then, well, if your message doesn't go under the target, you're out of luck. You need to find a new message. And so the nonce is just there to say, we can try again with a different nonce, and we can try over and over again. It doesn't...
Nonsense, right?
Sorry?
It stands for nonsense. I mean, the actual
Yeah, it is literally nonsense.
The proof of work is irrelevant.
Actually, unusually for cryptography, it doesn't even need to be random. It can literally be a counter. Yeah, it is just something that allows you to try over and over again. Okay, yes?
You had your first example where you had two people, the chain there. If these two people were both honest,
Yes.
so you try to record Tom gives Dick some money and the other one trying to record Anne gives
Yep.
Mary some money, one of them wins.
Yeah.
Now what? So what happens about Anne
Right.
giving Mary some money?
So what happens about this usually is once, well, so there are two alternative histories going on here. And so if this one says Anne gives Mary some money, and it's not in the top one, what's most likely to happen is someone will include it here. Now, it is possible, of course, that the top version of history makes it impossible for Anne to give Mary money because Anne's already given someone else the money. And in that case, Mary will never receive her money. So this is a reason to not accept immediately when you see this, or sorry, when you see this one on the bottom. Because it can still happen that the block you see turns out not to be valid. And I'll get back to this in a little bit when I talk about the formal properties that blockchains actually give.
Is that called an orphan?
Yeah, I think orphan is one of the terms for it. I don't really know the lingo that well.
What I'm thinking is if I'm the one that knows that Anne gave Mary some money and I don't get there fast enough and everyone else moves on,
Yeah.
don't I have to start encoding Anne gave Mary some money again on the next head and the next? So in the end I might never actually get there fast enough to record my transaction.
Yes. But the issue here is, well, the thing is the following. If Anne is sending Mary some money, then the traditional thing to do is broadcast that transaction to the entire network. And everyone that sees this transaction will, at least in theory, include it in a block. Now, your situation can happen, but that would require someone who has a large control over the blocks that are being created actively censoring the transactions. And that's something that we assume doesn't happen because we do assume that most of the blocks that are created are done so honestly. Okay. So, a little bit of a tangent on proof of stake. So one thing that was noticed early on is this process is quite wasteful. I think the first time I talked about this or something similar, I looked up the statistics, and Bitcoin alone was consuming on the order of electricity of Ireland. I believe this probably has grown since then. And it is one of the most, it's probably the second most ridiculous arms race the human race has perpetuated. There is no point in this. We are building machines that can do more and more hashes so that we can show we can do more hashes than the other people with bigger machines or with slightly smaller machines. There's no benefit in this at any point. It is, well, it is an arms race in its truest nature, and the observation of proof of stake is the problem here is that we're using external resources. And when we allow external resources, well, people can acquire more of those at the expense of, well, quite limited external resources that we have. So one of the core observations is we are already building currency systems. That gives us a very nice finite resource that we can quantify very well. So why don't we just assume honesty about that resource? Let's say in the case of Bitcoin, who owns how much Bitcoin, and work with that instead. And it turns out to be slightly more tricky than that easy way of saying it. So there's a couple of problems that crop up. The first problem is the so-called nothing at stake problem. And this is more of an observation that it's easier for someone to attack a system that has internal resources. If you have a system with external resources, if I wanted to do this attack, I need to make all of these blocks again. If I decide at this point in time I want to create an alternative history, I now need to catch up. And I need to put in that much work to catch up. In a proof-of-stake system, you can just see what would have happened in your alternative history. There is no cost to exploring it because it's not tied to any external resource. There's nothing you put into the system. You're just executing the system in a different way. Oops. So this, for a long time, people thought that this makes proof-of-stake impossible. Turns out that's not quite the case. It is actually very possible to do. But this fact that you can easily try multiple avenues of attack at the same time, and it costs you nothing, was something that, well, disconcerted quite a few people in the early days, and still now does, actually. The second problem is an interesting one, and is stake bleeding. So this relies on the fact that most currency systems that are built on top of blockchains have a fee system. So if I want to send you money, I will have to pay some small fee so that the network actually accepts that. And the people who create blocks usually get to harvest these fees and get to use them for themselves. Now, what this means in a proof-of-stake system is I can create an alternative history where I start harvesting everyone's fees over a very long time. And eventually, I'll have harvested so many fees that I have more money in my alternative history than people are actually using in the real history. And as a result, my alternative history can seem like it is more active and there's more going on in it than in the real history. Now, it turns out it's actually fairly easy to identify this. You just need to check at the initial point where these histories diverge, who is more active. And at that point, you'll very easily see, I'm not as active because I just can't create as many blocks. I can only harvest fees on some blocks, and you can observe that. And as it turns out, proof-of-stake is possible. I'm not going to tell you how it works because I need another lecture of the same length for that. But there are multiple systems that do it, including the Ouroboros line of protocols, which comes from this lab here, and the Algorand and Snow White protocols, which come from other labs. Now, finally, or actually not finally, now I also want to briefly talk about the different transaction systems on blockchains. And for the financial transactions, it's usually fairly simple. If you want to make a transaction, it looks something like, let's say I want to send you some money. I make a transaction by saying, please give 5 Bitcoin to your public key, and then I sign the whole thing with my own secret key. And this is then just broadcast to everyone and is hopefully at some point put in a block in the data section. There are a couple of subtle differences here. The differences mentioned here between UTXOs and accounts are really just, do I generate a new public key every time I receive funds, or do I reuse my public key every time? So they're not fundamentally very different. It's just a slight difference in the usage. What is more different is smart contracts, and I can't do them justice in this short talk either. well, it's not short, but I can't do them justice in the time I have either. But the idea behind smart contracts is essentially, whereas for currency systems you have a very well-defined rule set, so if I have a transaction that says I'm sending you 5 Bitcoin, that means my account balance goes down by 5, yours goes up by 5. For smart contracts, you can program arbitrary systems instead. So in particular, you can see the blockchain as a shared state, and smart contracts program a state machine over them. So that I can program, for example, a state machine for an auction contract, and then you make a transaction which says something like bid 5 Bitcoin on this item, which my contract knows to interpret. Now, as I said before, I could go into a great deal more detail on this, but unfortunately I don't have the time. So, getting back to the question of this very nice fraudulent transaction which never got adopted that we briefly discussed, the question is what do blockchains actually get us in a formal sense? And the key 2 properties they get us are persistence and liveness. So in particular, what you do not want is precisely this transaction where, I forget who it was, Anne gives Mary some money, and then it turns out later that that transaction never actually happened. And persistence is precisely the property that tells us when this can't happen anymore. And it says, if your transaction is more than k blocks from the most recent one, then everyone agrees about it. So this is really the consensus you get from blockchains. And so in this situation, the reason Anne sending Mary money could be reverted is because it was too recent. It was not within these k blocks from the end. And the second property is quite simple, and it just says, well, if I have a new transaction and I broadcast it to the network, sometime later it will be persistent. Now, these are underpinned by 3 more low-level properties, which largely express the same thing in different ways. So there's common prefix, chain quality, and chain growth. Common prefix is just really a rephrasing of consensus, and it says, well, if you have 2 users and you take both of their chains, you chop k blocks off the first user's chain, it will be a prefix of the second user's chain. And chain quality is a more interesting property because it actually talks about honesty of blocks. And it says, well, if you have a long enough sequence of blocks, there will be some fraction of honest blocks among them. Now, what's actually somewhat interesting is this is not necessarily the same fraction as you have honest miners. It's as actually you get closer to a half of dishonest participants in the protocol, this fraction gets a lot worse. So, but it turns out that up until a half, you still have some fraction of honest blocks. And the final property of chain growth just says, well, eventually you'll get more blocks. Yeah, that's pretty much it. All right. So this is it as far as the basic introduction goes. I'm now going to talk to you a little bit about privacy, which is my field of research, so I'm also going to be plugging some of my papers. But yeah. So a common misconception I get when I talk to people about blockchains is that they are very private. They're not. And I can kind of see where it comes from. Like you hear in the news about how, there are Bitcoin black markets, etc., and this kind of stuff. But they're only private they're only more private than fiat transactions in the sense that your bank is not involved. Now, that does get you some privacy, yes, in that there's no one that can assign a face to the transaction. Okay, but it is drastically less private in many other ways, because you're really airing your dirty laundry for the world. And a good way to picture this is you can picture any cryptocurrency as a type of cash. And worse than that, it is marked cash. And worse than that, it is marked cash which everyone knows how to trace at any point in time. So that means if I have a Bitcoin, I know who I got, or I don't know the face of the person who I got it from, but I can find out some information about them. I can find out some information about who they got it from. I can find out who they've also been doing trades with. I can find out who free links in the past received their money from some dodgy website, and how maybe I don't actually want that coin as a result because it might be subject to police investigations or something bizarre like that. And I don't think that that is a great state of being. So in the early days of research on this paper, A Fistful of Bitcoins, managed to link, I believe, transactions between many of the large entities in the Bitcoin network, including Silk Road, the notorious black market trading site in Bitcoin. And if I remember the story correctly, the owner of Silk Road could not actually cash out on his Bitcoin because doing so would reveal who he is to law enforcement. I realize that doesn't make a great case for privacy, but I don't really care. So the question is then, how do we make these systems more private? In the case of currency transaction systems, and in the case of smart contract systems, it's not even clear what we want to do. I described them as we program this public state machine. How do we take a public state machine and make it private? Well, I'll talk a little bit about that, but it's still very much an open question. So for private currencies, things are actually, at the moment, pretty much solved. In the early days, there were already solutions for this. So even back in the time that this linkage was made, people knew in theory how to deal with it. It's just in practice it wasn't happening. And the core idea was to do mixing. So it's quite simple, really. If I just go around this room and pass around a bag and everyone puts in a £5 note, and then I shake the bag thoroughly and I pass it back around and everyone takes out a £5 note, then suddenly the fact that you've marked the £5 is kind of useless because no one knows who has which £5 note anymore. And you can do the same thing in Bitcoin. It's actually quite easy to do, although it does require, scheduling ahead of time, and I'm not sure if it requires a trusted party to do the mixing or not. I forget that detail. But in practice, the barrier was too high and people don't do it. So there's still no privacy. Monero is I think the largest private, or selling itself as private cryptocurrency, which extends this in some way by saying, well, it's very difficult to get people to coordinate, to put their £5 in this bag and to actually regularly do this. So instead, let's just allow transactions in which you claim to have spent some £5 note from a group of people. And this is possible because of a very nice cryptographic primitive, which I never took the time to understand, called ring signatures. So please don't ask me any questions about that. But the basic idea is I can pick any number of you and I can say, I'm spending one of our £5 notes. And no one knows that it's actually mine I'm spending, because no one can identify me in this transaction. Now, that's very nice, but it still only gives you a statistical privacy in that you still have this set of people, and it's good for plausible deniability, but it may still, reveal statistical links which can be tracked over the long term. But what really solves this is the zero cash cryptocurrency. And for me to tell you how that works, I first need to introduce a somewhat magical piece of cryptography called zero knowledge. Do any of you know how zero knowledge works? Show of hands. One person. But I kind of expected you to know. So the basics of zero knowledge is if you have some NP relation, so some non-deterministic polytime relation, then you can prove a statement of the following type. I know a W such that XRW holds. And the key here is I'm not going to tell you W. I'm just going to tell you what X is and what the relation is. Now that seems a bit detached when you first hear about it, but one really cool thing you can do with this is you can prove that you know the pre-image of a hash without revealing it. And this is precisely what zero cache uses for its privacy. And zero cache essentially lets you say a fairly complex zero-knowledge statement in which you're saying, I am the owner of some coin, I prove that I know its secret key, and I also know that the serial number of the coin is this, where serial numbers are somehow unique for every coin that you spend. And then everyone else can verify this serial number has not been spent yet, and he has indeed proven that he knows of a coin for which that is a valid serial number. Therefore, he can spend it. So how does this look in practice? Well, you have two values. You have, two public-facing values. You have a coin's commitment. When you send someone a coin, you generate this from their public key, and from you again select something random, another nonce, and you select, you don't select, but this coin has some value. And you get to put these into a commitment, and this commitment is stored across, everyone stores this commitment and remembers this commitment is to a valid coin. So the currency system maintains a set of these commitments which are valid. And it also maintains a set of serial numbers which have already been spent. And now the key to spending one is to say, well, I'm proving for this set of valid commitments that I know a commitment which is in there, I know the corresponding secret key, and I computed serial number correctly, here it is. And just by the fact that you've proven that, and that that serial number has not been spent before, it makes you eligible to spend this coin. Is that too confusing? Someone's grinning. A little bit too confusing.
I understand the principle, but it's really hard to explain.
Well, this is the best I've got, sorry guys. So as a shameless plug, I extended this to do proof of stake over it as well. So using the same techniques to do a private form of proof of stake, which is not as easy. Well, I guess you probably didn't think after my bad explanation that it was easy, but it is harder than it sounds as well. So shameless plug, there's this Ouroboros Scripsinos, which got accepted at IEEE Security and Privacy this year. It's joint work with my supervisor, Agalos and Markov, as well as Vasilis Zikas. So now, it turns out this technology exists, and if you actually read better explanations than mine, and you understand it, and you try to, and you go through the proofs, and they make sense. This technology has been proven, it works. But unfortunately, people don't use it right. In particular, there are bad defaults, and as a result, you get people doing exactly the same linkage attacks as they did for Bitcoin. So in particular, the Zcash one, privacy is optional here. So you have to actually tick the box that says, I want privacy. Turns out users don't tick the box, and as a result, you can easily de-anonymize the private cryptocurrency. For Monero, I think it was a more complicated matter. Don't quote me on this, but I think the details were that the selection of the anonymity set. So remember, you select some number of people and you say, I've spent one of our coins, and the selection of this anonymity set was bad. So most people select the same people, and then it's very easy to identify the odd one out, which is then probably the one who's actually owning the money. So that's it for privacy and currencies. We've kind of got it figured out. For smart contracts, we still don't know what's going on. There are a couple of attempts to do things. The first attempt I know of is Hawk. And it kind of sees the situation of you have a public state machine and says, you can't really make this private. The only way you can make this private is by assuming a trusted third party. And they do that. They assume a trusted third party, and they trust this party with the privacy of the system. But they give fallback guarantees that if the party turns out to be corrupt, you still get the system working correctly, but you lose your privacy. More recently, I believe still unpublished, is an extension of zero cash called Zexa. So whereas zero cash requires you to prove that you have, or that you know the correct secret key corresponding to some public key, Zexa generalizes this and says you just have to satisfy some arbitrary predicate. And at least in theory, this lets you express much richer conditions as to when you can spend coins in zero cash. It's also not clear how this really interacts with end users and how people will, what people will do with this. So as my second and last shameless plug today, and also actually my reason why this presentation is not as great as it could have been, because last week I submitted Kachina to Eurocrypt, so fingers crossed about how that goes. And so this is my attempt to, well, have my say in this domain. And my core contribution is to say, well, the blockchain itself is a public thing, and yes, it induces some public shared state, which we have state machines over, but users can still have their own state. They can maintain their own private state, and they can, more importantly, interact with the public state in more subtle ways. They don't need to interact with it as directly as users usually do in typical smart contract systems. I realize that sounds very vague, but I could give a talk this length on that alone, so sorry about that. Finally, it's worth noting that privacy can be completely solved. And there is a very heavyweight cryptographic primitive called secure multi-party computation, which is essentially a magic bullet. It can solve this and many other cryptographic problems very easily. The core principle of this primitive is for any function you want, you can have any number of users compute this function where each user supplies one input to it. So if I have 5 users, each one can, the function would take inputs A, B, C, D, E, and each one of the users supplies one of those inputs. And then what secure multi-party computation lets you do is it lets every user find the output of that function without any user learning any other user's input. So this is a very powerful primitive, and well, you can quite easily build private equivalents of smart contracts with this. There is an enormous downside though, and that is it does not really scale very well. It is a very expensive primitive to use, and certainly at the scale we're using blockchain systems these days, it won't work out. Which brings me to my next topic. A second problem that blockchain systems face these days is scalability. This is a KN graph for n equals 7, and this is the network topology of every decentralized system out there. This is pretty bad. In particular, what this means for blockchains is, well, each of these edges is who you send transactions to. If I am this user here and I make a transaction, I send it to everyone. And in practice, it's not quite like that. You select a subset of the network and you only send to them, and they're responsible for forwarding. But even that concession actually weakens the network model we have. And the core observation here is, well, first off, this doesn't scale well. The more users there are, the more things I need to process. Okay, that's usual in every system, but usually you change the network topology to deal with it. You introduce some more centralized nodes which handle the bulk of the work. That is explicitly not possible here. We explicitly gave that up when we wanted to decentralize things. So, as a result, this doesn't work well if you want to put the world's transactions in it. And there are a couple of attempts to solve this. the first attempt to solve this is to lie about it. So I'm not going to name any names because slander law is a thing and I don't want to get stuck at the wrong end of it. But if right now you try to invest in the cryptocurrencies that handle the most transactions and boast being the fastest, you will find that all of them claim to be decentralized. You will find that quite a few of them are not. It turns out it is easier to build a, semi-centralized database than it is to build a fully decentralized blockchain. Now, as not to say everyone is liars, there are people that are actually doing things, and there are a couple of ways that you can approach solving this. And in particular, if we do need to have a KN network topology, then we'd best do our best to make sure that this network topology is utilized as well as possible. And it turns out that Nakamoto consensus does not utilize it well. In particular, first off, it's a stochastic process. You do not know when a new block will be found. And you cannot even make sure that most of the time blocks are being broadcast, because it turns out that the security guarantees rely on the fast delivery of blocks. So it relies on the fact that everyone gets the most recent block fairly quickly. So there's a couple of attempts to solve this. And actually, before I go to those, it's worth noting that for precisely this reason, there have been lengthy discussions over how large the blocks should be, because having larger blocks has the downside of it actually damaging the security of the system. And having larger blocks damages the security of the system, and it doesn't even get you that much of a network performance gain. You may go up from utilizing it, I don't know, 5%, no, probably even less, 2% of the time to 4% or something like that. Now, there are some attempts to solve this in better ways. So Bitcoin NG, I think, is the first I've read on this, and it takes a very basic approach of saying, well, if you have someone who's already created a block, you let that person send a bunch of packets containing transactions after it, so create essentially a series of small blocks in succession to keep the network busy. The approach of directed acyclic graphs essentially says, well, instead of having a linked list data structure, we can use a DAG instead, and then somehow agree on the ordering of things afterwards. So I believe there are a number of systems out there that actually do this, but I believe none of them have a complete security analysis. So, okay, that's not great. And what I actually find the most elegant solution in this space is just run a bunch of blockchains next to each other. Turns out that they even out statistically, and you can use the network in its fullness if you run 1,000 blockchains at a time. There is still a question of how do you get one consistent history from all of these, but it is still possible. Finally, when I was at IEEE Security and Privacy this year, I watched a talk on Perun, and I think they put this really in the best way, which is we can't expect to handle the world's data on blockchains. Google can't handle the world's data, and they can optimize their network topology for it. So instead, we need to consign ourselves to doing the bare minimum of what we need to. We shouldn't handle everything that goes through the system. We should only resolve disputes on a blockchain. And this is the core idea behind payment channels. It's still far off from that ideal, but the basic principle of how payment channels work, and this is something that is working right now. So in Bitcoin, there is the Lightning Network, which you can actually use. At least I believe so. I haven't used it myself. But the basic idea is if I want to more frequently do transactions with one of you, we can open a channel together. So, for instance, I can put down 5 Bitcoin and one of you puts down 3, and we open a mutual channel with a value of 8. This initially requires a transaction to be put on the Bitcoin blockchain, but after this initial transaction, we can trade money back and forth within the limits of this channel. So within the limits of 8 Bitcoin, where I start with 5 and you start with 3. And then at any point, if one of us wants to cash in, we can go back to the blockchain and we can redeem this. Now, this is very nice for, let's say, situations where you have large corporations which frequently send money between each other, but it doesn't really work well in the consumer model. I'm not going to put down £100 with my local supermarket so I can go there every Saturday. And so it's a bit ironic, actually, because if this is ever going to get adopted in a consumer setting, we will need essentially banks. And so we've come full circle. We've gotten rid of them with this wonderful new decentralized system. And now we're saying, well, turns out we can't scale that well. Can you come back, please? Can you please do this for us? But it's not all doom and gloom. It turns out we still do get a benefit out of it, which is the bank can't run away and steal our money. We can hold them to account, and well, arguably you can do that in the real world as well, but arguably you'll have a hard time if your bank does decide to steal all your money tomorrow. So, yeah. So, this is the end of my slides. I'm going to talk still for a minute or two, and I wanted to do the world's worst demonstration. Let me just figure out how to actually move this over. So, I wanted to talk a bit about the applications of blockchains. And when researching this talk, I decided I should search for applications of blockchain in case I was missing anything important. And I found this wonderful site, which tells me the many new applications of blockchain in the brave new world. And you find get lost. You find some sensible things like asset management, and I have to take care to click on the right ones, and cross-border payments, which are definitely things we can do. You find some very ambitious things, like governments with blockchain. Yes, try convincing your government to do that, but at least in theory, it's something I can see, having a public value to it and something that can actually be technically constructed. And then I see very strangely weird things like integrating our smallest devices in fully connected KN networks and putting our most private information into the most public systems we have constructed to date. And what I take from this is we are really struggling to find good applications of this technology. That's not to say that there aren't good applications. I think there are many things which benefit from it, but it's important to bear in mind what blockchains actually give you over, say, a database. If you have a database, you can do everything a blockchain does. The only thing you can't do is do it in a distributed setting. So you have to get something out of this distributed. And I don't think it's a coincidence that blockchains picked up in popularity around the time of the financial crash when trust in banks was at an all-time low. Now, I see that as indicating some potential applications. The reason I highlighted blockchain government as one of the potentially interesting ones is because trust in government is not so great. Another interesting one, there is a platform called Steemit, which attempts to do decentralized social media. It doesn't do it particularly well. A colleague of mine recently published a paper basically attacking their content selection algorithm and showing, well, you can get it to show whatever you want it to show so long as you have enough money. But in a world where Facebook is not very well trusted, yes, I can see that application. But Well, what I want you to bear in mind is if your colleague approaches you and says you should use blockchain for your great new project, maybe you don't need it. Maybe you're the next blockchain healthcare and people would rather you didn't. Yeah, that's all. Thank you.
So we have, thank you, that's brilliant talk. So we'll have a couple of minutes for take some questions. Any questions?
Yes.
Yeah.
Do you have any thoughts on security tokens? Just a way of, you know what it is. Security can explain it better than you. They're using them for people instead of doing an IPO for a company. They actually sell units in the blockchain.
And
Just
one
proof
thing,
of ownership without involving.
the one thing that we really have down these days in blockchain is managing arbitrary assets. And not assets that are tied to something in the real world, but just managing tokens, we're great at. We can spin up fictitious currencies as much as we want by now. And if you want to use this fictitious currency as your official token for some security, why not? It does give you quite a bit of flexibility. It essentially, well, it allows others to trade this in a very simple and straightforward way, and it removes your responsibility in managing how these tokens can be traded, and that there are now well-established standards. So I think security tokens is a point where this makes sense, provided you actually have some external source backing them, and they're actually...
Give me the Mona Lisa. Do you want to jump to that? You think art's
Right. Well, if the Louvre wants to put the Mona Lisa as a security token on the blockchain,
They've already taken it with
sure.
art, but it's the regulatory framework that's very ambiguous, and that's what is preventing me from doing it, any kind of token sale. Because if you get it wrong, at best you'll be shut down and struck off as a director, at least in this country. At worst, you'll end up in prison because you're issuing a security token that's not regulated. So until the government catch up and give us very clear regulatory guidelines, I'm not touching any kind of
actually, as an anecdote here, so I'm also involved with a blockchain company called UK. They are not involved with this talk, by the way. But from one of the things I've gathered with them, they're going to very great lengths to make sure they are not seen as issuing tokens at any point in time. So they're specifically setting up systems and protocols which issue tokens by themselves so that they don't have to do it. And it's precisely to avoid these ambiguities in legislation so that they can hold up their hands and say, we have never issued a single token.
Yeah, good luck. That sounds so sketchy.
Yeah, but put it this way, the cryptography works out, I don't care about the rest.
You mentioned the second arms race and
Yes.
energy consumption being at the island. With the carbon debate going on now in energy production, is the carbon issue going to eclipse this and stop it eventually? Because it's on an exponential growth curve, I understand. Therefore, it's not sustainable.
It's on an exponential growth curve and it's not sustainable. I don't know where it's going to go, to be honest. And the problem is at the moment it's profitable.
Yeah.
And if it's profitable, people are going to do it. Now there's several things that can be done to make it less profitable. One of the ironies was that in many of the places Bitcoin is being mined, energy is subsidized for corporations. So as a result, the government is paying for the Bitcoin mining, essentially. Now that's not the way it should be. So there's definitely things that can be done better there, but at a global scale also I don't know what's going to happen. It's hard to say. It's certainly a problem.
One more question?
It was just a comment from the live stream that you hadn't made any, you hadn't discussed voting systems on the blockchain.
Yes, I have not discussed voting systems.
And also someone had mentioned, I would have thought that after cryptocurrencies that would be an important area of development.
Sorry, but what would be an important area?
Voting systems.
Voting systems. So, I have not talked about voting systems because they are a research topic in their own right. And yes, you're quite right. It is an important system, or it's an important question. But Part of the reason I haven't touched on them is because right now cryptocurrencies are in a bit of an odd situation with voting systems. That if you set up a voting system over cryptocurrency, you're essentially on purpose setting up a plutocracy. And that's not something I'm very comfortable with. That said, there are definitely people that are working on this, and there are a great number of things you can do, both to make this voting system as flexible as possible and to make it private and to give various guarantees you want from a voting system, but it's really not my area of expertise. So that's the main reason I didn't talk about this, because it's not my area. But there is a great body of research on electronic voting in cryptography, and that is something that a lot of people have worked on a lot, and it's something that, at least in theory, we know how to do.
That's one question.
Yeah, I was just going to ask, I mean, you obviously kind of said that current blockchains generally rely on proof of work, i.e. proof of resource, and there's been research into proof of stake. Are you aware of any other mechanisms that they try to kind of develop similar systems with?
So there are a couple of others. The only one which I know of kind of working at the moment is proof of space, where you essentially prove that you have hard drive storage instead of proving that you have processing power. I'm not that sure of the details of how it works. But I do know that that is a thing. Off the top of my head, I can't recall any others, but I'm sure there are.
Or distributed proof of stake. Proof of authority is another one.
Proof of authority is one I deliberately didn't mention because it essentially boils down to the Byzantine generals problem again. So proof of authority is a term that people have given to where there is a fixed committee which decides on when to create blocks. And essentially at that point, yes, you have precisely the Byzantine generals problem. The old protocols that solve that will solve your proof of authority.
Trying to word this right. Would blockchain work as a store of attribute details, anonymized?
What do you mean attribute details?
So, I don't know, maybe identity, for example. So if we're looking to move, an identity of a person has lots of different attributes that basically comes together and identifies who that person is. So actually having it, the person anonymized by a hash or whatever, and then being able to store indexes to various different attributes that identify who they are, but still keep it cryptographically sealed.
Yeah, you could do this kind of thing. So for example, a government might conceivably decide to store a hashed form of, for example, your passport information in the blockchain, and you could then prove your identity via that. Although it's worth noting that really you don't need a blockchain for this. All you need is a distributed database, which is something that's simpler to construct. Because what blockchains buy you is a guarantee about the order in which things happen. And in the situation of identifying yourself, you don't actually care about the order.
I think Estonia is the first government to actually implement that.
Yeah.
I think they had actually done it, or they were talking about doing it.
I think they've got a form of it
Yeah.
in the distributed ledger end, not so much blockchain and...
It's distributed ledger is a more academic term for blockchain.
Yeah,
It's
few
the same thing.
slight differences, yeah.
Well, distributed ledger is a more general term.
Okay.
All right, take lots of questions. Is any here or no? I just have a question, and I'm quite interested if somebody said, I want to get into the Bitcoin market, start trading, and what your advice would be?
My advice would be to do your research and not to trust what I am saying. So in particular, I literally told you that I am affiliated with a blockchain company, so don't trust what I'm saying. Watch out for scams.
That's all I'm saying.
All right, thank you very much, and let's have another block. So the room booked at 8:30, so if you have more questions or you want hanging on, and we will be available to answer more questions. Thank you very much for attending, and hope you enjoy the talk.
Thank you for coming.